Hey guys, just want to remind you that we're getting really close to the end of the semester. After this chapter, we only have 2 more chapters. So we have, today is the 27th. We'll have a review on Wednesday for the test. We're going to wrap up everything for the test on today. And then we'll have a review on Wednesday. And then on Friday, we'll have the test. I'm not going to be here, but it'll be in the auditorium like usual. My wife will give it to you. She's better than me. So, she can answer any of your questions. And then we have just a week and a half, and then we have, our spring break, and then we have another week before our exam. Exam 4 right here. And then we'll cover that exam and review for the final on the last day of class. All right? That last exam will just be 2 chapters plus a little bit of this chapter. All righty. It's exciting, right? That's mine. Yes. All right. So we are having our test on Friday. Oh gosh, do you have an OpenStax due this week? You don't, do you? I haven't given you any extras. It was just that last one, huh? Yeah, so you're not going to have any of that this week. Just sort of focus on the test, all right? We're picking up with household and RC circuits, right? And then carrying on all the way up through mirrors. So when you get to the section on atmospheric phenomena, we're going to cover that today, but that won't be on the exam. We got enough stuff to worry about for the exam as it is. Okay? So let's wrap up this. We did these concave mirrors. When I have an object that's outside the focal point, it produces an inverted and a real image. It can be bigger or smaller or the same size. It depends where it is. But in this case, we drew the 4 rays parallel to the axis through the focal point. Through the focal point, where is it? Through the focal point, parallel to the axis. That was rule number 2. Rule number 3 was through the center of curvature. And I sort of fudged it a little bit. We just imagined our center of curvature was there. And then back upon itself. If you're careful with the ruler and all that, these all come out just right. And then the 4th one was to the center of the mirror, and then just follow the law of refraction. The law of reflection. So this angle is equal to this angle. And they should all cross where the image is. Now where the rays originate is the point on the image that crosses. So notice that I drew the guy upside down because the rays cross below the optical axis. This is the optical axis. You don't need to know that, but that's what we call it. And so that's why this guy looks upside down. Now if the rays had crossed up here, it would be an upright image. But you know what? An upright image isn't going to be on this side of the mirror because upright images are always what? They're always vertical, right? So an upright image would be on this side of the mirror. And we'll see that with a concave mirror, and we'll see it also with a convex mirror. Let's look at the other scenarios. You can have one that's inside the focal point. This one's a little trickier. And as I said last time, the way you'll see this in the exam is I'll give you a figure with a bunch of rays drawn on it, and I'll ask you to pick out the correctly or the incorrectly drawn rays. I'll show you a similar question later. But here, we can't get them all, but we can get some of the rays parallel to the axis and through the focal point. That was rule number 1. Rule number 2. We can't draw because it would have to go through the focal point and it's at the focal point and then parallel to the axis. Rule number 3 we can draw through the center of curvature and then back on itself. Let's see, I'll do it pink, I forget what I did before. So the way this works is I draw a ray as if it's originating from the center of curvature. So I draw a ray that goes up and like that. And then it's going to reflect back on itself. Now let me remind you the rule. The rule was the ray goes through the center of curvature and then it goes back on itself. And let me show you the one from the previous page. Just stay where you are. But remember on this one, the ray went through the center of curvature, which we said was right here, and then it reflects straight back on itself. And so this one's a little bit different, because I'm in front of the center of curvature, but I imagine that the ray is originating here. And it comes up, it hits the top of the object, and then it goes right there. And then it reflects back on itself. So this is ray number 3. Now notice here, that these rays are parallel. I can draw a third ray like this. All three of these rays, this is rule number 4. I just draw to the center of the mirror, and I let this angle equal this angle. And the law of reflection is followed for all of these. Like if I draw a perpendicular line here, then you'll see that the two angles are equal. Law of reflection is obeyed in all of them. But here it's easier to draw. So notice that these rays are parallel. Remember that when P equals F, which is what we have here, that I get 1 over F equals 1 over P plus 1 over Q. And if P is equal to F, I make that F, so Q goes to infinity. That means that there is no image. So remember when we did Tyler in the concave mirror, and out here Tyler was upside down? That's like the previous image that we did. And then as I got closer, there was a brief moment when he got fuzzy. Remember that? Yeah, I think did you see the fuzzy image? All right, that's the no image. That means that he was at the focal point. Right? And that's what you get here. All the light rays are parallel, so they never cross, and so there's no image. Let me write that down. Light rays are parallel and don't cross. So there's no image. All right, and then concave mirror object inside the focal point. This one's probably the trickiest of all. Rule number 1 is easy. I go parallel to the axis and then through the focal point. And by the way, let's just remember what we're headed towards. We're headed towards, if you remember from last time, we're headed towards a bigger image, an upright image. And you should remember that if it's upright, it also has to be virtual. And if it's virtual, that means it has to be back here in this space. This is what I like to call the virtual space of the mirror. A bigger, upright, virtual image. So this is ray number 1. Ray number 2 is kind of funky. I'm going to go through the focal point and then parallel to the axis. So kind of like what we did before, I imagine a ray coming from the focal point, like that, such that if you were to trace it back, it would go through the focal point. So I imagine that my ray is originating at the focal point, comes up to the top of the object, and then it goes on to the mirror. Through the focal point, and what? Parallel to the axis. This is like the reverse of number 1. Now right away I can tell that these rays on this side are divergent. So I get divergent rays on this side. And divergent rays are never going to cross in real space. However, we're going to do a thing that we've done before, where I trace these rays back, and then I'll be able to tell where the image is. So let's go ahead and do that now, and then I'll draw the remaining rays. I can trace the blue ray back. This is called a virtual ray. You can't project it onto another reflective surface or anything like that. It's virtual. It's in that virtual space, you know, where only like the poltergeist, the strange people can go. And then the red goes back like this. And so my image is going to be like this. Right? Bigger, upright. And because it's upright, it also is virtual. But remember with mirrors, virtual images are always opposite the image, opposite the object. Because in mirrors, this is our virtual space, this is our real space. This is the space where we can project onto a screen. This is the space where you can't project these onto a screen. Let's do 3 and 4 as well. Number 3 is through the center of curvature, and back on itself. So just like we did before, a ray that originates at the center of curvature and goes up like that, and then it reflects back on itself. So this is ray number 3. And then I draw it back, the virtual ray, and it crosses right there. And then ray number 4, I just follow the law of reflection, sort of like this. I can trace it back, and it looks like me in my new hat. You didn't get to see it, sorry. But, alright, you want to see my new hat? Y'all care? You don't care. Look. It's nice, isn't it? Yeah. A student made it. He did it. Isn't that cool? I think he did it. I'm pretty sure it's he said did it. We'll take it outside. No, I'm just joking. That was a joke. Don't tell anybody else. Or maybe it's what I mean. I don't know. It was Brennan. Was it Brennan you had the conversation with? Yeah, okay. Maybe that's what I mean. Anyway, so this is number 4. Okay? Listen, if you're not getting these, they're in the homework, so they're in the homework solution. If you want to go back and check them out, they are. Come see me. But again, I'm not going to ask you to draw them, but I do expect you to know the rules. And it helps to know what types of mirrors produce what types of images for the test, too. And then convex mirrors. Remember, convex mirrors, the focal point is behind the mirror, so the focal length is negative. Anything that's behind the mirror has a negative value. If my image is behind the mirror, the image distance is negative. If my focal point is behind the mirror, then the focal point is negative. If the object was behind the mirror, it would also be negative too, but we won't find that with mirrors at all. Okay, so then if f is negative, 1 over f, this is a negative value, 1 over p plus 1 over q, what does that tell us about the image distance? Well, it tells us if this value is positive, the only way to make this value negative is that this value will also be negative. So with convex mirrors, if the focal length is negative, then q must also be negative. All right? So we're looking for then a virtual image. And this is like a security mirror, right? I've seen those big security mirrors. I brought one in last time. But a security mirror, like at, I don't know, they don't have them at Walgreens. They have flat mirrors at Walgreens. But at various convenience stores and stuff, sometimes you see them in parking lots. Those images are smaller, and they're upright. Okay, so these rays look like this. Ray number 1 is through the focal point and parallel to the axis. This one's tricky. The way you're going to draw this is you'll draw a ray number 1 through the focal point and parallel to the axis. You draw a ray such that if you were to trace it forward, it would go through the focal point. That's the incident ray. A ray that if you were to trace it forward, it would go through the focal point. And then it goes parallel to the axis. That's ray number 1. Ray number 2, what was it? Parallel to the axis and through the focal point. Parallel to the axis. Look, this type of device, we'll see this with lenses, but I'm going to tell you the word now that you don't need to know for the test. This type of device is called a divergent device. That means it causes rays to diverge. So I know that this ray is not going to bend down like this. Instead, the ray is going to go up in this direction. And you can think about the law of reflection, that this is my incident angle right here, so my reflected angle has to be here. That can also help you on the test, because you can look at the incident and reflected angles for the correct or incorrect rays and sort of gauge those that are just grossly wrong. So here, this one is going to reflect off of the mirror like this. Hold on, don't draw that yet, because there's more to it than just that. Reflects off the mirror such that if you were to trace it back, it would go through the focal point. And so that's ray number 2. That's what it means, parallel to the axis and through the focal point. But it's actually the virtual ray that goes through the focal point. And so now we can trace back ray number 1 as well. And now we know where our person is. It's right here. Virtual, smaller, upright, just like we expected. So those are rays 1 and 2. 3 and 4 we'll do similarly. 3 is through the center of curvature. But we draw a ray such that if it were to go forward, it would go through the center of curvature, like that. And then it goes back on itself. So it goes back on itself and it goes off into space. But then we trace it back, the virtual ray, like that. This is ray number 3. Notice it also crosses right there. And then finally, ray number 4 is go to the center of the mirror and check that these angles are equal, and then you can trace this back. And your image is right there. That one's a little tricky because you got a lot of virtual rays, and then you have a lot of rays that are sort of originating from different points. But the words of the rules are still fulfilled. That I'm going parallel or through the focal point, sort of, and then parallel to the axis. I'm going parallel to the axis and then through the focal point, but it's actually the virtual ray that goes to the focal point. Then I go through the center of curvature, sort of. I trace it forward, and then it reflects back on itself, one big long line, and then I follow the law of reflection. But they must always give you a virtual, smaller, upright image. So you can also look at where those images are formed and make sure that it's forming the right kind of image. Let me just recap the 4 different types of images that you can get with concave mirrors. If you're outside the focal point, then you produce a real, inverted image. All right, that means that if this is my object, this is my image. A real inverted image. The real image is on the same side as the object. If I'm at the focal point, I get no image at all, because the rays are parallel. And if I'm inside the focal point, I get a virtual upright. All upright images for mirrors are virtual. A virtual upright bigger image. This is like your shaving mirror, right? That mirror that I brought in, the concave mirror, it's just like a big shaving mirror. You can't really see the spherical surface of your shaving mirror, but if you look at it closely, you can sort of. That's why you get that magnified image. And if you have one of those makeup or shaving mirrors, try setting it on the table and then backing up a long ways from it, 10, 12 feet, and then your image will flip. Because it has a focal point too, it's just the focal point is a lot longer than the one that we have. All right, that's all for concave. For convex, anywhere you are, it doesn't matter, you get a virtual, upright, smaller image. So the way you'll see this, one, on the word problems, where you have to use the mirror equation, we're going to do some more today. But sometimes you need to know what type of image is formed by what type of mirror. Or you need to be able to tell what type of mirror it is based on the type of image that's being formed. And so knowing these 4 different types of images that are formed will be essential, actually, to working some of those questions. I'll show you one in just a bit where that's necessary. You'll also have questions like this, where I'll show you a mystery device. It'll be a mirror, not a lens in this case. and I'll tell you where the object is, and I'll show you a sketch of the image, and I'll ask you what type of mirror produced this. So let's try this one. I'm going to have to pull up my clicker base, sorry. All right, so what type of mirror produced this image? Is it a convex, a flat, or a concave? Or could it be either convex or concave? All right, let's stop at 50. Stop at 50. Okay, very good. A is right. That is a convex. It's a virtual upright smaller image. Let's see. Oh, why did the stadium get hot after the game? All the fans left. Okay. Which of these mirrors will produce a virtual image under particular conditions? Concave, convex, or flat, or some combination of those? All right. Okay, doing pretty well. Let's stop at 1 minute. Or we're going to 105, 105. Okay, A is right. Concave produces a virtual image only when you're inside the focal point. Convex produces a virtual image always, no matter where you are. And flat always produces a virtual image. Remember, P was equal to negative Q. So Q is always negative for a flat mirror. It's always a virtual image. All right, let's go to the back of your book and do some more practice problems. I want to show you some different types of problems. Let's see. Like this one, for example. This is what I mean when I say I'll show you an image with certain rays, and then you'll have to pick the correct or incorrect rays. In this one, I want you to pick out the incorrect rays. The incorrect rays. This is exam 3, if I'm not mistaken. Which are drawn is incorrect. All right, let's stop at 2 minutes. 2 minutes. It's 10 more seconds. All right. I don't think that's right. So let's see. So let's look at ray number 1. And not rule number 1, just ray number 1, right? I'm going through the center of curvature, and then it falls back on itself. That's correct, right? No? Ray number 2, where was that one? Right here. It goes through the focal point, and then parallel to the axis. That's right. Ray number 2, it goes through the focal point right here, comes into the mirror, and then it goes back parallel to the axis. And now let's look at number 3. Maybe a lot of y'all can see. 3 is right here. It goes parallel to the axis and through the center of curvature. Y'all are correct, or at least that number 3 is wrong. So C is the right answer. Sorry I doubted you. I thought it was easy. So C is the right answer. Now some of you put that 1 was incorrect, but 1 is correct. It's not the rule number 1. That's what you were thinking of there. It goes through the center of curvature and then it reflects back on itself. Something like that, guys, is what you'll see and how I want you to know these, okay? Let's see. You'll see some simple problems like number 26. Let's just try out number 26. A concave mirror has a focal length of 10 centimeters. Notice I didn't tell you if it's positive or negative, and I never will. All right, so you'll need to decide, is it positive 10 or negative 10? An object is 10 centimeters, where is the image located? She's using the mirror equation on that one to find the image position, Q. Free to ask your neighbor. All right, I'm going to stop at 105. 105. Look at y'all. C is right. Right, you should be able to look at this and say, gosh, look. The object is located at the focal point. So I have my concave mirror, and my object is located right there. And you say, well, that's one of my 3 scenarios. So it has no image at all. So C is the right answer. Let me ask you another question. This is very important. If you're American when you go into the bathroom, and American when you come out of the bathroom, what are you while you're in the bathroom? European, right. Who said that? Camille, was that you?
No.
Who was it? Megan. Anyway, sorry my international students. I don't think I have any European international students. What? Okay, let's try one more. Let me see if I can find one. Ooh, too far. So the test that's in the back of your workbook is a good indication, at least, of the material that you'll see. Let's look at number 24. So number 24, I don't tell you what kind of mirror it is, but knowing what kind of mirror it is actually fairly important. Number 24. Produces an upright image, and then I tell you, it's to the left of the mirror, the object, the image, or the object is to the left of the mirror. Where is the image located? So think of all the information I give you, tell me what kind of mirror it is, and then calculate the image distance. All right? Oh, no, maybe a little bit longer. Go ahead, keep going. It's okay. All right, let's stop at 2:05. 2:05. 10 more seconds. Okay, good. A is right, I'm pretty sure. We want to sort of look at the clues here. I know that the center of curvature is 8 centimeters, so that tells me that my focal length is either plus or minus 4 centimeters. It will be negative if it's convex, but if it's concave, it's going to be positive. But then it says it produces an upright image. That means it could either be convex or concave, but the object is 8 centimeters high. This is the object. And the image is 16 centimeters high. So this is the image. This is the object. This is the image. So I know it can't be a convex, because convex mirrors produce images that are smaller, right, like the security mirror. So I know it has to be a concave mirror. So by doing that little bit of sleuthing, I figure out that my focal point is actually positive. But if it was convex, you know, it would be a smaller image, and then that would clue me into it being a convex mirror. Okay, so my focal length is that, positive 4. The object is 8 centimeters. No, that's not what I want. Sorry. Well, this is tricky. And then the magnification is HI over HO, right? So the magnification is 2, right? 16 over 8, and that's also equal to negative Q over P. All right, I'm going to erase some of this. Glad y'all did so well on this. This is not an easy question. Y'all know the answer before? Because y'all are awesome. That's what it is. All right, so I take my mirror equation, 1 over F equals 1 over P plus 1 over Q. I have 2 unknowns, right? I have P and Q are both unknown. So I have to substitute one equation into the other. You can do this a couple of different ways, but let's just say that Q is equal to negative 2P. You see what I did there? I just solved that equation for magnification for Q. And then I can take that value for Q and put it in right here. And now I have an equation with just one unknown, and I can solve that. So I get 1 over F, which is 1 over 4, equals negative 1 over P. Is that right? 2 over 2P minus 1 over 2P. Sorry, did I do that right, y'all? 2 over 2 minus, it should be 1 over 2P. That's right, right? Am I with me? You with me? No. I'll go back over it. Let me finish and I'll step back through it, okay? And then I solve this for P. 1 over 4 equals 1 over 2 times 2. So P is equal to 2. And then I plug that in up here, I get Q equals negative 2 times 2 is negative 4. So it has to be 4 centimeters to the right of the mirror. Is that what y'all put? It is. Good job. Let me step back through this, okay? Because there's several processes that go on here. First thing to do is identify what type of mirror it is. And I identify it by looking at what type of image it produces. It produces an upright image. That doesn't help me a whole lot because it can be either concave or convex. But then it also produces an image that's bigger than the object. And in fact, it's bigger by a factor of 2 because 16 over 8, HI over HO is equal to 2. And then that tells me that I have a concave mirror. And since it's concave, the focal length is plus 4. Now I got this because it told me the center of curvature is 8. And this focal point is half the center of curvature. So it's going to be half of 8 is 4 plus 4 because it's a concave mirror. Now I have two equations, this one and this one, and I have to substitute one into the other in order to solve it. Because I don't know either Q nor do I know P. So I take this and I say Q is equal to negative 2P. I just solve for Q. I do that because I don't want to deal with a fraction right now. So I could have said P was equal to negative Q over 2, but I didn't want to do that. But you can do that, that's not wrong. And so I take this P, negative 2P for Q, and plug it in right here. And then this equation becomes one that only has one unknown in it. So then I solve that equation for P, and then I can go back and I can find Q. So lots of different steps that go on in a question like this, all right? But you will likely have a question something like this on the test. Maggie?
Can you explain what you got when solving?
Yeah. You want me to solve this? Is that what you're saying?
Yeah, like I don't understand.
All right, let me give a little space. I think you're not the only one that's confused about that. So I have this equation, 1 over F equals 1 over P plus 1 over negative 2P. I need to find a common denominator, right? And the common denominator is 2. So I have 2 over 2P minus 1 over 2P. So I have 1 over F is equal to 2 minus 1. 2 over 2 minus 1 over 2 is 1 over 2P. All right, and then I know that F is equal to 4. And you could cross multiply. You could say 4 is equal to 2P. P is equal to 2. Or you could just say, this is 4, this is 4, so just P is equal to 2. And then take that P equals 2, and we've already established that this is true. If P is equal to 2, then Q is equal to negative 4. All right? Right. Negative 4 is a virtual image. Right. And so it's 4 centimeters to the right of the mirror. The object is over here. The image is over here. And it's a concave mirror. Okay? You have some homework questions that are similar to this that solve systems of equations. I'll try to give it to you so that the numbers are easy. Okay, but you will have one probably like this. Okie dokie. So be prepared to practice that. Alright. Oh, you're not going to have any like this. Number 20 and 21. Although we are going to cover that now. That's not going to be on the test. It'll be on the next test. Okay, that's going to be the breaking point for our test. That's because we have a lot of information on this test. Can I go up from here? Go back to the... Is that okay? Is today Monday? It is Monday, isn't it? You had a good weekend? You have your scrimmage? No? Yeah? Who won? Nichols? Yeah. Did your team win? Awesome. It's because you're the best one, right? Yeah. Okay, let's look at atmospheric refraction. Again, end of the exam. That's the end. This is exam 3. And here on out will be exam number 4. Okay? So if you see anything about atmospheric refraction or atmospheric phenomena, not on the exam. But I do want to go ahead and cover these because we have 10 minutes and just sort of get them out here. We have two phenomena that occur because of the refraction due to the atmosphere. One is that the sun appears at dusk, even though it shouldn't, even though it's really below the horizon. So next time you're out at sunset and you're looking at the beautiful sunset, right, and you're with your friend or your significant other or whatever, just totally ruin the moment and say, that's not even the sun. It's just an image of the sun. It's not doing much for me at all. Because what happens is, we're sitting on planet Earth. We're up here in Alaska or wherever, and if we're such that we can't see the sun, right? Rays from the sun cannot reach us because we got this big section of the planet that's blocking our view of the sun. This is at dusk, at sunset. However, the rays from the sun, the way they bend, they come into the atmosphere and they actually bend around until we can see it for a certain amount of time, not an insignificant time, 10, 20, 30 minutes maybe. Where the sun is actually below the horizon, but you can still see it. So that's one thing, that's one phenomenon. And the second is that you see mirages on a hot day. That road over in Raceland, when you go past the sugar plant, that road I'm talking about, it's all bumpy, that little shortcut to get to 90. That's a really good place to look for these. On a really hot day, like in July or August, go out there and you're driving down that long straight road, and you can see off in the distance they look like what? They look like what? Yeah, it was like big puddles of water, right? Here, and you're like, oh no, you're gonna crash. But then you get up to it and they disappear. And then you're just dumbfounded. Right? Y'all have had this experience before? We have no idea what just happened to that huge puddle of water. Well, it was a mirage, everybody. Now you know. It was just a mirage. And what happens is that light rays near the hot ground are refracted. They're bent. Because light travels at different speeds in gases of different temperatures. And so a light ray would come down, and then it would hit that hot air, and it would actually bend up and bend towards you. But you don't know anything about the light ray bending, so you think that instead that it's actually the light ray is actually originating from some reflection. And when we think reflections, we think, oh, there's a puddle of water. And so your mind makes that connection that, oh, there's a reflection out on the road of the sky and the trees and stuff, then that must be a puddle of water. So this looks like a reflection. So you assume that the object, which is the camel in this case, but most of the times it's just the clouds in the sky and maybe some trees or other cars or whatever, that is standing in water, which reflects. However, mirages are not a result of reflection. In no way are they a result of reflection. Nothing about them is reflection. They're purely a refractive phenomenon. All right, a couple of clicker questions, then we'll watch that video. And let's try these. Which of these physical phenomena is the cause of a mirage? All right, let's stop at 30. 30. What? Okay, got it. Crying out loud. Y'all ready? Okay, good. A is right. It's a refraction phenomena. It's not reflection, not diffraction, not interference. Hey, do you know how you find Will Smith in the snow? Y'all might not get this. You look for Fresh Prince. Do y'all get that? Y'all know what I'm talking about? Oh, okay, good. Is that show still on? It's not on, is it? It reruns. Okay. What causes a mirage when you see while you're driving on a road? We'll stop at 25. 25. All right, very good. A is the right answer. It's the refraction of light in warm or hot air. It's not a reflection, and it's not the refraction of light at your windshield either. It's the refraction of light in the warm air. Did y'all know that we had a seminar on time travel last Tuesday? That's not very funny, is it? Not funny? You already get it. It's time travel. We're gonna go, but it was last Tuesday. Huh? We'll work on my delivery a bit. We are having a seminar in a couple of weeks on protein kinases. You know what I'm talking about? Biology thing, I think. I think that your cell class, if you're in cell, they might require you to go. But it'll be April 11th. We'll send you more information about it later. If Earth's atmosphere no longer existed, how would the time of sunset be affected? Would sunset occur earlier? Would it not change? Would it occur later? Or was there no way to tell? All right, let's stop at 30, 35. Okay, good. Sunset would occur earlier, because, as soon as it went below the horizon, you wouldn't be able to see the sun. Did y'all know that I used to work at a calendar factory? True story. But I got fired. I don't understand why. All I did was take a day off. Okay, so that's the end, and I think we'll just wrap it up there. But on Wednesday, we'll just do a review. Okay, remember this stuff on refraction stuff, not on the exam. But on Wednesday, come with your questions for the exam, and we'll review that. A lot of stuff on this exam. Have a great day.
Thank you.